Okay, so today I'm going to be showing you how to calculate the force on the side of a dam from the water if the dam has a trapezoid face. So first, I'm going to go ahead and draw the face of our dam, trapezoid. It's going to have some height, capital H. The top is going to have some width, capital T. The bottom is going to have some width, capital B. And then we're going to have some water level up against our dam. And that water level is going to be represented by small h. And we're going to go ahead and say that at the top where the water level is, that's going to be h equals 0. And then at the bottom, we're going to have the point z. So height equals z at the bottom, so our depth is z. So in order to find the force, we can use our force equation, F equals pressure times area. So we know the two things that we need to find are an expression for pressure and an expression for area. So let's go ahead and start with pressure. We know that pressure is equal to your atmospheric pressure plus rho GH, which is the density of the water times your gravitational constant times whatever depth you're at under the water. Now, because we're not working with the ideal gas law, we don't really have to worry about atmospheric pressure. We can go ahead and work with gauge pressure. So we can just cancel our atmospheric pressure out, which leaves us with pressure equals rho GH. So because we don't have any atmospheric pressure, our pressure at height equals 0, or wherever our water level is, our pressure there is also 0. So now that we have our expression for pressure, rho GH, we can go ahead and work on finding an expression for the area underneath, the area of the trapezoid face underneath the water level. So I'm going to go ahead and draw our trapezoid again a little bit diagonally, and here's our water level going up against the dam. So we can split our dam up into very thin slices, with each slice having a height of dH and having some width r. So we can say that the area of any one of these slices is equal to width times height, or r times dH. So now that we have an expression for area and pressure, you're probably going to want to, plug those into your force equation. However, we have to be cognizant of the fact that as you go up the dam, the width of your slices actually decreases because it is a trapezoid. So if you take a slice towards the bottom, it's going to have a much larger width than if you were to take a slice at the top. And so the width is dependent on whatever height you are on the dam, or some expression r of h. So we need to find some expression for r of h in order to account for this changing width as you go up or down the dam. So we can say that at height 0, and I know that we are using a height of 0 to represent the water level as far as h goes, but just for finding our function, we're actually going to use a height of 0 as the base of the dam and move up from there, because if you have a water level of 0, your water is going to be all the way down here at the bottom, and as your water level grows, you're going to need to account for smaller and smaller slices as you go up. If we were to use 0 as being the top here, as we get a higher water level, we would actually be starting from the top and integrating downward. So we need to use 0 as our height for finding this function. So we know that at a height of 0, the width of our slices will be capital B. And we know that at a height of capital H, or the very top of the dam, the slices are going to have a width of capital T. So because this width changes linearly as you go up or down the dam, this expression has to have some sort of slope. So the way we're going to find slope is the same way we do it for any other equation, rise over run. So we can go ahead and do T minus B over h minus 0, which is the same thing as just T minus B over h. So as you start at the bottom and go up, the height will change, or sorry, the width of our slices will change at a rate of t minus b over capital H. So we're ready to write our function now. R of h is equal to, starting at the bottom, b, plus our slope, t minus b over capital H, times however high up you are on the dam, h, or height. So we have an expression for our width, and we know our height dh, so we can go ahead and plug r of h directly into r. So we can write the area equals b plus t minus b over h times h, all that multiplied by dh. So now we have an expression for pressure, and we have an expression for area. So we can plug those into our force equation and work out an integral. So we know that dF is going to be equal to pressure times area. We have our pressure expression of rho gh. And that's going to be multiplied by our area expression, which is b plus t minus b over h times small h dh. So now we can go ahead and integrate this function. So the integral on this side is going to be for force. We're going to go from 0 to f of x meaning the total horizontal force that is pushing on our dam wall because of the water. On the right, we're going to integrate from 0, wherever our water level starts, all the way to the point z, which will give us our full height of the water. So once you go ahead and solve this integral, you're going to get the following. F of x equals rho times g times z to the third times 2t minus 2b, that quantity is going to be multiplied by z, plus 3 times h times b, all of that over 6h. So using this equation, as long as you know your width at the top and the bottom of the dam, and you know the height of the dam, you'll be able to find that horizontal force from the water pushing on the wall of the dam for any depth z.